Okay, all right. So today we are talking correlation and linear regression. And so this is chapter 4. It is week 2. um, it's only the second week, but I feel like we've been in class for a while already. Okay, so today's, topics are describing associations and relationships between numeric variables. We'll talk about correlation, the correlation coefficient, the number there, and then we'll also talk about linear regression. Okay, now I don't want us to lose sight of the big picture. And again, the big picture in statistics is that we are making conclusions from data. And before we can even start to make conclusions, we have to be able to describe our data, right? And then we got to understand probability. And so we'll start probability on Wednesday. But today we're still learning how to describe data, okay? And last week we looked at chapters 2 and 3, and we were describing data just one variable at a time. So in chapter 2, we described the data with pictures, we had histograms, we had dot plots and things of that nature. And then in chapter 3, we described data using numeric summaries, things like the mean and the median for where the center is. And we used standard deviation, variance, range, and IQR to describe how spread out the data is. Okay, so that was what chapters 2 and 3 were. We were just looking at describing our data one variable at a time. And today in chapter 4, we're still describing data, but this time we're looking at the relationship or association between two numeric variables. So we'll take a look at that. Okay. So what happens is, when we gather data, we often record multiple variables for each observation, right? So, for example, in your lab, you were looking at this North Carolina births data set. Each observation was a birth, okay? A mother gave birth to a child, and we recorded several variables. We recorded the mother's age, the father's age if we knew it. We recorded the weight of the baby, whether the mother was a smoker or not, things like that, right? So there's like multiple variables that that we are recording. And so, another example is maybe we record information about houses in a certain neighborhood. So imagine there's houses, and you can record how many bedrooms and how many bathrooms. But let's just say we measured the size of the house, okay, measured in square feet, and its estimated value, right? And what you'll see is you'll see a general trend. Generally, houses with higher square feet, okay, bigger houses are going to have higher value. Smaller houses will have lower value, right? And so we'd say there's a relationship between the size of the house and the value or the price of the house. All right. And today, what we're going to learn is we're going to learn how to quantify that relationship, okay? And so rather than just saying things like a bigger house means higher cost or higher value, we can specify things like if you add and not if you add, but an additional square foot of size is associated with an increase of, say, $350 to the value of the house. I'm making that number up, but it might be something along those lines. Okay, and so we're going to quantify it and specify actual numbers here, rather than just saying bigger houses cost more, smaller houses cost less. Okay, so just kind of one example that I'm going to load up is the average age of first marriage. Okay, so this is coming from the government website, the Census Bureau. All right, and they've recorded each year. They've recorded what is the average age of first marriage. So all the people who got married and things like that, they record, what was the average age. And so in 2019, for men, the average age of first marriage was 29.8 years, and for women, it was 28.0 years, okay? And this is not necessarily this person married this person. This is just the average of all men who got married and the average of all women who got married. So, that's just whoever got married, whether they were, to each other or not, okay? And they've been recording kind of this data, I think about every year since, I don't remember when, but prior to the annual thing, they did it kind of every 10 years, and so it goes back to 1890. In 1890, the average age for marriage for men was around 26 years, and for women it was around 22. In 1940, it was down to about 24.3 years for men and 21.5 years for women. So, and that was the average. So that means some got married later and some got married earlier as far as the average age went, okay? And so if we plot this, so it's important to note that each observation here is a year, okay? It's not a person. I think in the textbook there's a similar example where they're looking at different states, but here each observation is a year. And what we're seeing is that this is kind of the relationship for the men's average age of first marriage and the women's average age of first marriage. There's a very clear relationship, okay, in general, as when in years where the man's age was high, those tended to also be years where the women's average age of first marriage was also high. And in years where the average age was quite low, for men was quite low, the average age for women was also quite low, okay? And there's a very, almost like a very clear straight line relationship here, okay? Yeah, there's a few exceptions, okay? But there's very, it's a very clear straight line, not a whole lot of scatter or variation around such a line here. Okay, so I think I've written that. I wrote, there's a very strong relationship between men's average age of first marriage and women's average age of first marriage. In year where the average age of men's first marriage is high, the women's average age of first marriage is also high. And when it's low, it's also low. Consistently, if you look at it, there's about a 2-year difference, okay? There's a few exceptions. I think this is 1890, where the average age difference was around 4 years, but in general, there's around a 2-year difference. But of course, this is just the average overall, not, of course, individuals. Some will will have greater or smaller differences, and some will be older or younger than the average when they first get married, okay? These are not the only 2 variables in the data set, right? So in the data set, we have year, we have men, we have women, okay? So here I plotted men's age versus women's age, but here I can also plot the year where the data was recorded versus the men's age, the year where the data was recorded versus the women's age, and we get similar, slightly different graphs, okay? And so it looks like it recorded data maybe every decade until maybe around the 1940s, 1950s, okay? And then after that, it looks like they recorded every single year. And what we see is we no longer have a straight line relationship. It looks like from around 1890, which is when we first have data recorded, 1890 to around 1960, the average age of first marriage for men seems to continually go down from around 26 down to around 22. Okay, it goes down. And then, so in 1960, this seems to be around the lowest. the average age of men's first marriage was around 22 years, and then it seems fairly consistently every year after that, it's gone up and up and up until around present day, where the average age of first marriage is closer to 30. Okay. We have something similar for women, but for women in 1890, the average age of marriage was around 22, and it seems to have gone down until around 1960, where the average age of first marriages looks to be around 20 years old, and then every year after that, consistently going up and up and up and up. Okay, so and it's different in different populations and segments. So this is for the United States, and where I grew up, very well. I shouldn't say not where I grew up, but many of my peers went to college, and when you go to college, it's difficult to get married during that time, and so I knew very few people who got married straight out of high school, but my wife, a lot of her peers got married right after high school, so we kind of came from kind of different stories and different demographics, and so it's interesting, just kind of the different trends and things that happen. So again, this is just an average for that year. Okay, so in these plots, we would still say that there's a very strong relationship between the year and the average age of first marriage. Okay. But in this case, the relationship cannot be described with a single straight line. We can't just draw one straight line and say this summarizes all of the relationship of the entire data set, right? We see it goes down from around 1890 to 1960, kind of the first 70 years, the first half, and then from 1960 to 2020, which is, I guess, the remaining 60 years. So it's kind of from 2020 to 1960, that's the same distance from 1960 to around 1900. So, the first half and the second half, are kind of, they form almost like a V, right? So anyway, that's so that we could start off just kind of describing these relationships, just kind of describing the overall trends. Okay. And so I'm going to kind of formalize how we might go about describing a relationship. Okay. And so the three things, the key things that we want to talk about would be shape, trend and direction, strength, and then I should actually add a kind of a fourth line, anything outliers. I should add that. So let me add that. Doing this. All right, let me do. So I'll add a slide to our notes here. Okay. All right, and so I've taken these pictures straight from our textbook because they do a good job of explaining the idea. And so, when we talk about shape, as far as this class goes, we're going to describe relationships as linear versus nonlinear. Okay, linear means the relationship can be summarized with a single straight line. It doesn't mean that all the data have to follow exactly a straight line. And so this is, I think this is like internet searches for the words vampire and zombie, and they were looking at kind of how like on Google Trends and stuff, you can kind of look at like dates where a certain word was searched a lot or infrequently, and there seems to be kind of a linear trend. Okay, and then nonlinear would indicate that the relationship cannot be summarized with a single straight line. So here is the dots that appear, and we would need some kind of curved line. Okay, so this would be nonlinear, and this would be linear. Okay, so and as far as this class goes, we're going to say straight line versus something that's not a straight line. You know, if you choose to major in statistics and you want to create more trend lines, then this nonlinear would probably get broken out into, you know, logarithmic and quadratic and different kinds of, you know, further. But, you know, as far as our intro stats class goes, we've just got linear versus nonlinear. And then we want to talk about trend and direction, okay? So as far as direction or trend goes, there's positive trend, there's negative trend, and then we have neither positive nor negative, okay? So if you have a positive trend, that means the large values of x are generally associated with large values of y, and small values of x are associated with small values of y. So the age of marriage thing, if x and y are the average age of men's first marriage and average age of women's first marriage, you know, the x and the y have a positive relationship. Okay. Negative is just kind of the opposite. Large values of x are associated with small values of y, and small values of x are generally associated with large values of y. And we'll have an example of that. And then you have neither positive nor negative, which is basically neither. Okay. So here we have a positive trend between, if you're thinking of, you know, how much a car is worth and how old it is, or I'm sorry, not how much it's worth, but how many miles has been driven on the car versus the age of the car, we're going to see a positive trend. Okay. Older cars that are high in age, will tend to have more mileage driven. Okay. And newer cars, age near zero or age low age, will tend to have fewer miles driven. Okay. So we've got a positive trend. All right. And of course there's exceptions, like here's a car that's 22 years old and, you know, comparatively it's got relatively low mileage, but and then here's a car that's only maybe 5 or 6 years old and it's got very high mileage. But overall there's kind of this general trend going from the lower left to the upper right. The negative trend, on the other hand, is goes in the opposite direction. So we have we're looking at different countries, okay, and so kind of across, and it might even be across time. I'm not 100% sure, but we're looking at the literacy rate, okay, and total births per women, okay. So what we see is, you know, when a country achieves 100% literacy rate or something very close to it, in general, there tends to be fewer total births per woman, okay? So this is kind of the measure of quote unquote fertility. And of course, it doesn't necessarily mean every single woman in that country is giving birth to this many persons, but just overall on average, you know, if one person has zero children and another has 2 and another has 5 or whatever, you know, you just kind of take the average. And so here we have a negative trend. So over here, this would represent countries or times where there was lower literacy, and we have higher total births per woman. Okay, and this is just literacy rate. This is of the general population, not necessarily of one specific gender or sex, but just overall literacy rate. You know, there's a negative trend. Okay, now we have to be careful not to make a cause and effect conclusion about the association between these two variables. There's definitely a negative association, but you know, it would be dubious of us to say that literacy rate, like if we get people to read, then women will have fewer children. Okay, that, you know, I mean, it might. I don't know. I don't know how all of these things go. Sorry, my Wi-Fi cut out. I have not given any quiz answers yet. Okay, I've not given any quiz answers yet. So the literacy rate itself may or may not have a direct effect on the number of births per woman, and more likely, okay, and the data does not reveal this, all right. It's more likely that there's a confounding variable, okay. There may or may not be a confounding variable that's causing the variation in both variables, right? So is literacy rate is kind of a proxy for just having an educated populace, and why would having an educated populace lead to lower total births per woman? This is a complicated question, and the data in of itself is not able to answer why. All we can say is just, yes, there's definitely an association, and that's so you want somebody who's a little bit more knowledgeable in terms of kind of sociology and those dynamics working together. I guess I might as well give the first quiz answer. So the first quiz answer for today is E as in elephant. First quiz answer is E as in elephant. Maybe I'll kind of do it again in about 5 minutes or so, the first quiz answer again. All right. And then if it's neither positive nor negative, you might have something like this, right? So here is some data where we're looking at a bunch of marathon runners, and we're looking at the age of the runner and how long it took for them to complete the marathon, okay? So, the marathon is what, 26.2 miles. A lot of people take around 4 hours, 5 hours to finish, somewhere between 3 and 5 hours. And what we see is that, as far as the people competing in this marathon in Forest City, it's not like, it's probably not a super highly competitive one, not like the Boston Marathon or something. And so you have, young people, in their 20s who take a short or long amount of time. And then you have older people in their 60s who take a short or long amount of time, people in the middle who take a short or long amount of time, right? And so we don't have an association where we could say older people take more or older people take less time in general, okay? Just in general, some people take less time and some people take more time, and it doesn't seem to be affected by age. Here's kind of another example of neither positive nor negative, all right? There's definitely an association. There's definitely an association between the two variables, right? And this is just made up data. So, as x goes in this direction, it goes up, and as x goes in this direction, it goes in the other way. There's definitely an association, and we could draw kind of a curved line that runs through the middle of this, but the overall relationship is neither positive nor negative, right? If you split the data at x equals 0, right, if you draw a vertical line kind of in the middle, this half has a negative relationship, and then this half on this side has a positive relationship, okay? But overall, the entire data set is neither positive nor negative. I kind of want to do like one more example here. Let me... All right, so here's I could have another plot. If the data goes like this, okay, this too would be neither positive nor negative. Let me see. There's something wrong with my pen tablet here. All right, and so this could be something like income, and this will be number of fingers, okay? And so, you know, depending on your data set, and I recognize not everyone has 10 fingers, but perhaps in your data set, based on the people you've collected, all persons had 10 fingers, and you looked at the income level, and what we see is there's no association between income level and the number of fingers that that these people have, right? So that would be another example of neither positive nor negative. All right, so does that work for vertical as well? Yes. So I could just swap the axes, right? And I could have a number of fingers and income. And then your data would look like this. And this is neither positive nor negative either, okay? Yeah. So if there's no association between income and number of fingers, there's not going to be an association the other way around. Okay. I will repeat the first quiz answer. The first quiz answer is E as in elephant. I'm just repeating myself just in case you stepped away for the one moment that I gave the answer away. So E as in elephant for the first quiz answer. I'm just repeating myself. All right, let's talk about the strength of a relationship between two numeric variables. Okay, and so if we're looking at the strength, we can use words like weak or strong. And what these words do is they describe how much scatter appears in the scatter plot, or how well you can make a prediction for one variable based on the other, right? So, so here we can look at two variables and look at the relationship between a person's height measured in inches and the person's weight measured in pounds. And we can also look at the relationship between the person's waist size, so how how big their waist is, versus their weight in pounds as well. And what we see is in this scatter plot, there's less scatter, right? There's these are more spread out vertically, okay? And here there's less scatter, and therefore we would say the relationship between waist size and weight appears to be stronger than the relationship between height and weight, okay? So there's more scatter, so this is a weaker relationship, less scatter, indicating a stronger relationship, okay? And if we had to make a prediction for weight, knowing someone's waist size, we're likely to make a slightly more accurate prediction than if we knew their height, okay? In both cases, you have a positive relationship and a looks to be a linear relationship, in that, larger waists are associated with greater weight, smaller waists with less weight, or higher height is associated with higher weight, and shorter height, lower height, associated with lower weight. But there's a difference in the strength here. Okay, so both have linear relationships, both have positive directions, but different amounts of strength. Okay, so here we're looking at again, men's average age of first marriage and women's average age of first marriage. And so if someone were to ask you to describe a relationship, kind of mentioning the three things that we were talking about, that is the direction, the shape, the direction, and the strength, we might say something like this. The association between average age of first marriage for men and the average age of first marriage for, oh, this should say women, that's a typo, for women is positive and linear, okay? Years where the men married at an older age tended to be years where women married at an older age. The association is strong because there's very little vertical variation in the graph, right? So this almost fits like a perfect straight line, with the exception of these couple of years here. Very little scatter, so we would say very strong relationship, okay? When you're describing a relationship, use words like tends to or in general, okay? Because the relationship, there's definitely going to be variation and variability in the data. And so individuals, for individuals, that relationship might not be true, right? Large X tends to go with large Y, or, whatever the trend is, it might not necessarily be true for, one particular observation, okay? And then if there's any observations that are really unusual or don't appear to be part of the general pattern, it's good to kind of point those out and say, this one's, you might look at, countries and, their population versus GDP or something, or, number of cases or whatever it is. And whenever you do something where you're mentioning countries, there's two countries, China and India, that have incredibly high populations compared to the rest of the world, okay? And so, they almost always form a bit of an exception, just because, on a scale of compared to everyone else, they're, in general, like 10 times bigger, at least for most other countries, right? The United States comes in third at, 300 million, which is still, 1/3 or 1/4 the size of India or China. So that's how we would go about describing a relationship. All right, and so now we will continue on and talk about correlation. Okay, and so so far we've just been kind of using these words and kind of vague descriptors like strong and weak when we were describing a relationship. Okay, and we're going to introduce a statistic of value called the correlation coefficient that quantifies it, okay? So it's a lot like in chapter 3, we had numeric summaries. So rather than saying there's a lot of spread in the ages of the DMV room and there's little spread in the ages of the second grade classroom, we can specify it with the standard deviation. We can say the standard deviation is 18 for the DMV, and then the standard deviation is 0.6 for the second grade classroom, right? And similarly, rather than just saying there's a strong relationship or there's a weak relationship, we can give it the correlation coefficient, okay? And the correlation coefficient uses the symbol R, okay? R for like relationship. And it measures the strength and direction of a linear relationship, okay? Let me add that. I have a couple typos to fix. Okay. And so the correlation R is always between -1 and +1, okay? R that is close to -1 or +1, so R values that are far from 0 indicate a strong linear association, and R values that are close to 0 indicate a weak linear association. And then I will just add one more bullet point, and the sign of R is the direction. So if R is positive, the direction is positive. If R is negative, the direction is negative, okay? But you've got R values that are far from 0, close to +1 or -1 will be strong. R values close to 0 will be a weak relationship. So here's Here's an example. If they are in a perfect straight line, okay, so R values of 1 and -1, okay, you will get R equal to 1. So this is a perfect positive linear relationship, right? So these dots are in a perfect straight line. There's no scatter. And so you would have correlation equal to 1, right? This rarely happens in real life. Here the example is if we measure someone's height in inches, we could perfectly predict their height in centimeters, because all we're doing is we're just going to multiply their height in inches by 2.54. So if we know their height in inches, we can perfectly predict their height measured in centimeters. And they would lie in exactly on a straight line. If you had if you had just kind of the opposite, say it asks, does R value close to 1 mean a strong positive linear relationship, and R value close to -1 means strong negative linear relationship? Yes. Yes, the sign of R is the direction of the relationship. So if we had so if you had data that go in a perfect straight line like this, okay, R here is equal to -1, right? So you have a perfect linear relationship. Negative direction. All right, so you have, so there you go, right? So here's some other example pictures of just like different values of R. So here R is 0.72, here R is 0.48, here R is 0.19. So this is, what's the relationship between height and weight? 0.72. What's the relationship between, I guess we're looking at different cities across the nation, and what's the basically how much income does the city take in, and private income, meaning I think this is like businesses and stuff, and then the math SAT score versus GPA, weaker relationship, R equals 0.19, right? And in all of these we have these are all positive. Okay, we didn't show any plots of R being negative, but in general, as R increases, you get less and less vertical variation. They form kind of more of something that looks more like a line. And as R goes down, you get something that looks a little bit more like a blob or cloud of points, right? Okay. So to calculate the correlation, all right, technically this is the process. Both the X and Y values are converted to Z-scores. They're multiplied together, and these products are kind of added up, and then you divide by n-1, right? In practice, no one calculates a correlation by hand, okay? And we're not going to bother going through this process of calculating it by hand, right? So in general, we almost always use a computer to calculate correlation. I guess there's some fancy calculators can also do it if you take the time to punch in all of your numbers. In R, it's very simple. You just take the function correlation and you do x comma y, correlation of x and y, where x and y are kind of vectors. And so here I'm taking kind of the column of men's average age of first marriage, This is the column of women's average age of first marriage, and I'm asking what's the correlation between these two numbers, and we get 0.985, okay, which is very high. It's very close to 1, and again, you know, it's not a perfect straight line, so it's not 1, but it's pretty close to a straight line, and so we get something very high. Correlation of 0.985, okay? And it's very easy. All you do is you just type in correlation. You give it the name of your x vector and the name of your y vector. All right. Maybe I should say this is an important slide. I'll do that. No, I hesitate to do that because that would imply the other slides are less important. But it is true. This slide is important. Okay, so these are rules about correlation. So changing the order variables does not change R. So if height and weight have an association or correlation of 0.72, then swapping them, weight and height would have the same correlation of 0.72, okay? Adding a constant or multiplying by a positive constant does not affect R. So if you change the units, or if you add or subtract a value to everything, that's not going to affect the correlation. So changing your units from, say, centimeters to inches is not going to affect it. If you change your temperature readings from Fahrenheit to Celsius, that's not going to affect correlation, right? Here's a plot. Okay, so here correlation is equal to -1. All right. Oops. All right, so here's my question. What is the correlation of this plot here? So we have data where what is the correlation here? Is okay, all right, so you guys are okay, a lot of people are putting in the chat -1, -1, -1. Okay, very good. Okay, R is also -1. Okay, so correlation is not affected by slope. The slope is definitely less, okay, but correlation is not related to slope. Okay, this description, perfect linear relationship, negative direction, works just as well for this second picture as it does for the first picture. All right, and so so that's fine. Okay, but if I make it flat, okay, what would the correlation here? What would the correlation be? And here the answer is the correlation would be 0, right? So as soon as if it becomes flat, then there's neither a positive nor a negative relationship, right? So here, R is equal to 0, right? So, if your data lie in a straight line, these have correlations of -1, and here, the correlation would become 0, and as soon as it has a positive slope, then the correlation would become +1. Okay, so slope is unrelated to correlation. Okay, R is unitless. Okay, so there's no, you can't have a correlation of like $0.3 or something. It's just two variables. It's the correlation between them. There's no units associated. Okay, and the interpretation of R is only useful for a linear relationship. Okay, so the result of the correlation calculation, there's a formula and you just plug numbers into it and it spits something out. So technically, you can calculate the correlation for nonlinear relationships, okay? But the interpretation is not going to be meaningful, okay? A correlation of 0 does not mean that there's absolutely no association. but it does mean that there's no linear association, right? So if I go back to, say, slide 17, okay, or I should say slide 18, okay, slide 18, there's definitely an association between X and Y, okay? There's definitely association, but it's not a linear one, okay? All right, so has a nonlinear association, but the correlation in that plot would be 0. Okay. And so it's important that you should always graph your data first before computing R to make sure that the association is linear, right? So it's important that we kind of create a plot just to make sure that it makes sense to use correlation in the first place. All right, how are we feeling? Pretty good, I hope. Hopefully. Let me give you the second quiz answer. Second quiz answer is C as in cat. C as in cat for the second quiz answer. C as in cat, second quiz answer. And then why don't we go ahead and take a short 5-minute break. So we'll come back in about 5 minutes, and we'll finish out our lecture in 5 minutes. But we'll take a break. So I'm gonna pause. Okay, so now so we've talked about correlation, and we have this number R to kind of summarize the correlation there. And now we can talk about linear regression, okay? And so linear regression, what we do is we create a line, okay? We create the equation of a line, and it's a way for us to kind of describe the relationship, and it gives us an equation that describes the relationship. And it's a useful tool for as far as making predictions go, and for understanding the relationship between variables. And when you create a linear regression line, the linear equation is going to have the form y hat is equal to a plus bx. All right, and y hat represents the predicted value of y. And if you think back to your days of algebra, you basically have a slope right here and an intercept and a slope. So I think in algebra it was y equals mx plus b. And in this class we're going to use y equals a plus bx. And here the slope is the letter b and the intercept is the letter a. Okay, the slope is whatever is being multiplied by x, and then the value that stands alone is going to be your intercept. And so this is going to be the form of the linear equation, and this is going to be able to describe all of the relationships that are linear, meaning that we can kind of summarize them with a straight line. We're going to be able to kind of come up with an equation to describe that relationship. Okay. Now, as again, this linear regression is the simplest form of regression. Regression is a very powerful tool and kind of a favorite among statisticians, in that it is very useful for making predictions of a particular variable and for understanding relationships. And if you were to major in statistics, you would take an entire class on regression, where you're going to use multiple variables, explore relationships that are nonlinear, and things like that. And you can certainly make this equation a lot more complicated as time goes on. But as far as this class goes, we're going to just look at the simplest form, which is kind of this simple linear regression where we just have a straight line, and this is what our equation looks like. But this is it's a very flexible framework, and we can make things a lot more complicated if we want to. But overall, it's kind of primary uses are making predictions and then for understanding the relationship. So we'll take a look at that. All right. Depending on the textbook that you use, you might have a whole bunch of different names for the variables, right? And so when we're looking at linear regression, we use the x variable, okay? So we know the value of the x variable, and we're going to use that value of x to make a prediction for y, okay? So we're going to use the x to predict y. And so the other names for the x variable are things like the explanatory variable, the predictor variable, the input variable, the independent variable. I'm not a real fan of the independent variable name. And then other names for the y variable are things like the response variable, the predicted variable, the outcome, or the dependent variable. And again, the last ones, independent variable for x and dependent variable for y, I don't like those because in the next chapter, when we talk about probability, we'll talk about independent and dependent events. And so those words take on specific meanings to me, and they don't quite fit when we're using x and y variables. But they do appear in the literature, and those were the terms that were used when we looked at things in like high school for me. And the other thing about dependent variable is that the word kind of implies a cause and effect relationship, like the y depends on x, and that's not necessarily the case. There might be an association between x and y, but it might not necessarily be a cause and effect relationship. So anyway, I don't care for those words, but they do appear in the literature, and so I got to mention them. I think explanatory and response is are my favorite choices there. All right, so here's an example. We're looking at, I guess, sale prices of cars and the values of cars, and we're looking at how old these cars are and how much money they are worth. And I don't know, I'm not sure in what land the 15-year-old car has I don't know, has this much value. But anyway, this is what the relationship is, and here's the data that we've gathered in the blue dots, and the overall relationship can be summarized with this straight line. Okay. Now, obviously, it doesn't predict everyone perfectly. Okay. Obviously, this the line predicts for a 7-year-old car, the value should be, I'm just eyeballing this. So the car is what, 7 years old. It looks like it should be valued, what, $13,000 or something like that. 8 years old, it should be valued, I don't know, $12,000-ish, something around there. Okay, but we see exceptions, right? So here's a car, 8 years old, and it's got a lot of value, $25,000. Okay, and here's a car, 7 years old, and it's worth a lot less than what the line predicts. Okay, so it's not gonna be a perfect prediction, but overall, to summarize, it's useful in that it kind of just summarizes how it should be, and we can say that, you know, I don't know if you ever tried to buy or sell a used car, but you know, there's kind of like, there's guidelines, right? There's like the Kelley Blue Book value, and then there's, you know, other places where we'll say, you know, a car with this information should be worth about this much, and then you kind of look around and you say, oh, here's a car and it is on sale for something that seems a lot lower, so it seems like a good deal, I should get it. Okay, whereas if you're the seller, you want to be able to sell your car at, you know, higher than what the Blue Book says. You can say like, oh, you know, my car is special and it should be worth more than whatever this is, right? So but as far as the Blue Book value goes, it's useful to just kind of say, you know, this is what the overall relationship, overall trend should be. Okay, and so here, this is kind of what the predicted value equation, the linear equation might be. We might say the predicted value is equal to 21,375 multiplied by 1215 times age. Age is measured in years, and the value is measured in dollars. And so if we wanted to use this to make a prediction, we can say, let's predict how much a 12-year-old car is worth. we would just plug in 12 for age, 12 years in age, and then we do 21,375 times 1215 times 12. 1215 times 12 is 14,580, and you take that difference and you'd say the 12-year-old car is worth around $7,000, $6,795. Okay, that feels kind of generous, but this is just a prediction. Okay, and the actual car itself, if you have an actual car that's 12 years old, its value might be higher or lower than this number. Okay, so this is what we've got. All right. Here we'll look at a kind of a made-up data set. Okay, a very small one. All right, and this is how you might create a linear regression equation in R. Okay, so here I create a data frame. All right. So I create two vectors. I create the vector for height and a vector for weight, okay? And then I put the two vectors together, the weight and the height, into a data frame. And what we're gonna do is we're gonna try to predict the height, okay, based on the person's weight, okay? It's not a good idea you're going to get very inaccurate results, but this is just for illustrative purposes to try to say, all right, based on this person's weight, let's try to predict their height. Okay, and so that's what we're going to do. All right, and so we have 6 data points, and here they are plotted, and we have, you know, at least for these 6 data points, we have a positive relationship, and this is what we've got here. Okay, and so to do it in R, we use this function LM. LM stands for linear model, and it's going to be used to create kind of linear regression equations. And inside LM, you write the relationship, okay? And so here we write height tilde weight. And what this tells R is, it says we want to predict the variable height based on the variable weight, okay? And that's how we write this. We write height tilde weight. If you wanted to predict weight based on height, you would write LM weight tilde height. So the one that comes before, in front of the tilde, is the value that you want to predict. We are predicting height. And then the variable that comes after the tilde is the variables that are being used to make the prediction. And so this is how we do it. Okay, so we're going to call LM is height tilde weight, and we specify the data frame. Data is equal to dat. All right, so we've created the data frame right here, and then we're going to store the results of the linear model into I create a new object called model. Okay, and we could specify this to whatever we want to call it. Okay, but here I've just decided to call it model. And so when we call, when we ask what is the result of model, it prints out, it tells us what the intercept and the slope are, okay? So the intercept is our A value, okay? That's the intercept. And then over here, this is the slope associated with the variable weight, okay? And so this is going to be our B value here. And so our intercept is 52.397. Our slope is 0.08595, 0.86 if I round off. And we would say kind of our prediction line is height is equal to 52.397 A plus B times X, right? B is 0.08595 times the weight, right? And so it's very simple in R. You just type in LM and it outputs the results here. If you wanted to plot that line, okay, so you create the plot, and I think you guys know how to do this, right? You give it the x vector, the weight, and height is the y vector, and then here you can give it labels for the x label and y label, axis labels. Here I'm using plotting character 19, which is the solid dots. And then to draw the fitted line, you say AB line, okay? AB as in intercept and slope, which we have the AB line, and we're going to plug in the name of the model that we created, right? So you have to create this object, the result of a LM thing. So we stored this as model, and so we're going to say plot the line associated with the model, and I gave it the option color equals red, and you could choose whatever color you wanted, and here's the plot of the line, okay? And this works for any kind of regression line thing. All right, so R makes it very easy, and other softwares, I don't know if you've used Excel. Excel makes it pretty easy as well. But we're not using Excel in this class. So do I mind going back to the previous slide with the model commands? Yeah, absolutely. Okay, so the command is LM for linear model, and inside the parentheses, you specify which variable is being used to predict. So the one in front of the tilde is the value you are predicting. We are predicting height. And then the one after the tilde, after the squiggle, is the variable we are using to make the prediction, the x variable. So we are using weight to predict height, okay? And that goes inside LM. We specified the name of our data frame, right? So I think you guys are familiar with that. I think in your first lab you had like data is equal to NC births and things like that, I think. And then we store that using kind of the arrow. We say save it into this thing model, okay? And I think you'll see this in lab 3. So this week you've got lab 2, which you'll use to kind of like subset and do some logical calculations, but not but you won't be creating linear models just yet. I think that'll be next week. All right, and then you can create a plot. All right, if you needed to, you could find the slope and the intercept of the regression equation yourself, okay? And in order to do that, you would need these 5 summary statistics. You would need the mean of x, which is x bar, the standard deviation of x, which is written s sub x, s subscript x, to say this is the standard deviation of the x variable, the mean of the y values, y bar, and the standard deviation of the y values, s subscript y, the standard deviation, right? The symbol for standard deviation is s, and then to indicate it's the standard deviation of y, we write s sub y. And then you need the correlation between x and y. And again, we kind of glossed over this, but we said you just use the computer to find the correlation. And yeah, we're not going to bother calculating the correlation by hand. You can expect, maybe on the midterm, I will ask you to find the slope and intercept using the summary statistics. Okay, so you can expect this kind of calculation, which is fairly simple. Calculating the correlation by hand, I won't ask you to do. Calculating the slope and intercept, that'll make an appearance. Okay. All right. So, I'm just using R to calculate the mean and standard deviation. If we had to, you guys have learned how to calculate the standard deviation by hand, right? It's a little bit tedious, but if you had to, you could calculate the standard deviation by hand. But here, I'm just providing them right here. So we say, give me the mean. You guys know how to find the mean. You add them up, divide by n. Standard deviation, you find the mean, you subtract the mean from everything, you square all of those differences, add them up, divide by n minus 1, take the square root. It's a bit of a mouthful there. But if you had to find the standard deviation, you could. It's right here. Okay, here's the mean, here's the standard deviation, and then here's the correlation. Okay, so here we've got our 5 summary statistics, and now we can calculate the slope and intercept. All right, here's the equation for slope. Use your TI-84. That's fine. Yeah, I know. I think some of your calculators, you can punch in things and it'll give you standard deviation. That's fine, okay? If you make a mistake though and you don't show any work, in the grading of the quizzes, they can't give you any partial credit. That's just how it's gonna go. Okay, but here's the slope. the slope is b, and it's the correlation times the standard deviation of y divided by the standard deviation of x. And I think from the previous slide, yep, standard deviation of y is 2.607. Standard deviation of x is 26.7286. The correlation is 0.8809336. I just rounded that off a little bit. And so here our slope ends up being this, okay? And then the intercept, you got to find the slope first. The intercept, a, is equal to y bar minus b times x bar. And if you plug in b right here, and you plug in x bar 135 and y bar 64, this is what you get for the intercept. All right, and you can just combine these two together to get your regression equation, right? So back here, your regression equation is just the combination of the intercept and the slope times x. Okay. So if you had to, you can get the slope and intercept yourself. Okay, how's all of this feeling? Do you feel okay? Yeah, okay. Thank you. Thank you for those of you who are saying yes. Great. All right, and so we've already seen this, but I want to introduce this concept of a residual, okay? So here is the regression equation. Height is equal to this, 52.397 plus this times weight, and therefore we can make a prediction. So if somebody has a weight of 170 pounds, our prediction for height is going to be 52.397 plus 0.08595 times 170, okay? And so we would predict the person has a height of 67.0085 inches, okay? In our actual data set, we do have a person whose weight is 170 and the person's weight is 66 inches, okay? So there's a difference between this is what we predicted and this is what their actual value is, okay? So this is the actual value. So the residual is the difference between the actual value and the predicted value, okay? So the residual is the actual, which is 66, minus the predicted value, 67.0085, and so we get a residual of negative 1.0085, okay? And so this is the residual. The residual is the actual minus the predicted. I got a question here. It says, on the midterm and final, will we be expected to use RR Studio to compute certain things? When doing the quizzes, it seems straightforward in terms of showing our work by hand on the quiz sheet. But how would that work if we compute things with R? Okay, so on the midterm and final, it's going to be more similar to the quizzes, except it's going to be multiple choice, okay? And that just kind of helps with the grading, keeping things the grading fast. So I'm not going to be, so if you have R questions on the midterm and final, what it will be is I will show you some output, right? So I might show you like here would be a fair question. Like you might see output like this, and I would say, okay, based on this output, right? I wouldn't provide this thing, right? I would expect you to be able to figure out this equation based on this output. And I would say, based on this output, what would the prediction, what would you predict the weight or the height of someone who weighs, I don't know, 170 pounds to be, right? So with this output, what is the predicted height for someone who weighs 170 pounds? And so I would expect you to be able to go from this output to this equation. And once you have this equation, I would expect you to be able to plug in the number 170 and give me the predicted height of 67 or something like that, okay? So it would be, so in terms of how this would work on an exam is I would either show you the output of R and maybe some graphs or something, and then I would ask you to kind of make sense or use it in your calculations. But I wouldn't ask you, you're not going to have questions where I say like, what is the command that you would use to type this out? Okay, it's more so can you interpret the output of R? Because I think that's a lot more important, right? As far as like commands go, so I teach R classes and I teach Python classes, but there are many times where I'm just like, I forgot the name of the function, and I have to go on Google and I say like, how do I do this in R? Or how do I do this thing in Python? And so, you know, I'm not going to expect you to memorize every single R command, and the quizzes and exams are open note anyway. But I do expect you to be able to read the output from R and make sense of it. That to me, that's a lot more important than remembering the exact name of the function. Okay, yeah, I hope that makes sense. Okay, so anyway, this is what we call a residual, right? So, you know, why does this? Well, okay, sorry. Let me. I'm getting ahead of myself here. Okay, so so the residual again is the difference between the actual value and what we predicted. So we predicted 67. The actual value was 66. We have a residual of -1. Okay. When you create the linear regression line and you have the slope and the intercept, and if you use the slope and intercept as you follow this formula, or if you ask R to do it for you using LM, okay, this linear regression line has the property that it always passes through the point X bar, Y bar, okay? And so what that means is that if you have an observation of X, like a new observation, and the X value is average, meaning it's X bar, then your prediction for Y is it's going to be average. Y, our prediction for Y is going to be Y bar. Okay, and that makes sense. An average X should correspond with an average value of Y. Okay? And then the other property of the linear regression line is that it will minimize the sum of the squared residuals. Okay, so here we talked about the residuals being the actual minus the predicted. You can also think of the residual as the vertical distance from the line. Okay, and this linear regression line will produce, is going to have the minimum sum of squared residuals. And what does that even mean, right? But it's true that no other straight line will produce predictions with less total squared error. Okay, so let me show you a diagram on this website, this cool little website. And what is going on? Can't I see this thing? Something. Windows are acting funny. Okay. Can you guys see this? I hope. All right, so here is a data set where we have people's hand size and their height. And in general, people with bigger hands are taller and people with smaller hands are shorter. Okay, that's what appears in this particular data set. Okay, and this line represents the linear regression line, okay? Or a potential linear regression line, I should say, okay? And these are actually little dials that I can kind of rotate, okay? And this represents the intercept, and this represents the slope, okay? And so when I change the intercept, what that's going to do is it's going to slide the line up or slide the line down, okay? And so I can slide it up or I could slide the line down, okay? And then when I change the slope, it's going to change, either make the line flatter or make the line steeper, okay? So there it gets flatter and there it gets steeper, okay? All right, so what is going on with these boxes, okay? So what we're seeing, okay, is this line represents what our prediction is. And then this dot is the actual value. And therefore, the vertical distance from the dot to the line is my residual. So from this green dot to the red line, that vertical distance is the residual. And what it does is it's taking that that distance and it's making a square out of it, okay? It's basically, literally, it's squaring that distance. It's squaring the residual. And the area of this square represents the squared residual. And so every dot has its own vertical distance. It has its own residual. And we are squaring that distance, okay? So this brown dot has a residual, and we square that, okay? And this is how big it gets. This pink dot is very close to the line, so its residual is very small, and when we square it, it's about this big, okay? Now notice when I change if I shift the line to be way up here, we can see the distance from this blue dot to the line gets huge, and its square area is huge, right? So this has the total size of the squared residuals is very, very big, okay? And over here, as I move my line about, different sizes of the squares, squares all change size because, you know, as I slide it down or slide it up, it becomes, it predicts this orange and green dot very well, so they have very small residuals, but it does a bad job on the brown dot, and so it has a very big residual, right? Over here, if I slide it down here, it does a good job predicting the red and blue dots, but it does a bad job of predicting the green and orange dots, and so the green and orange have big squared residuals, the blue and red have small squared residuals, right? And so, and I can adjust the slope, and we can get different things. And basically, you could try like adjusting using these knobs to adjust how big the slope should be and how big the intercept should be. You're twisting these knobs, and the end of the story, at the end of the day, the least squares regression line is going to be, so if you pick 0.81, I don't even know if I can do it, okay, and 5.0, I don't think I have the fine-tuning ability to. Okay, something around here. This is going to be the smallest amount of residuals. Okay, so the line that has this slope and this intercept will be the line that produces the minimum sum of squared. I want to show that minimum sum of squared residuals. Okay, so this is this will be the smallest amount of residuals that we can have. And so, so sometimes you will hear a linear regression also called least squares regression, because it's getting at the idea of having the smallest squared residuals there. The least squares. It's the one with the smallest amount of squared residuals. Okay, I hope that makes sense. All right, so that is kind of the technical things of that, and so so we can make predictions, and we want the line that kind of produces our best predictions by having the smallest residuals there, squared residuals. And the other aspect of using linear regression is that we can understand the relationship between the variables. Okay, so here's a wall of text. And so if we look at the example with weight and height, okay, here our slope is 0.08595 and our intercept is 52.397, okay? And so I'm just for simplicity, I'm going to round off the slope to 0.86, okay? And what the slope tells us, the slope is how much our prediction for y changes, okay? So our prediction for y changes when the x variable goes up by 1 unit. So whatever unit x is measured in, when x goes up by 1, the slope tells us how much our prediction for y changes. So when we're talking about weight and height, the slope is around 0.086. Height is measured in inches, and x is measured in pounds. And so that means when the x, or the weight, goes up by 1 pound, our prediction for height goes up by 0.086. That's the direct interpretation, okay? Now it's important to note that when we say when the x variable goes up by 1, we're not saying that we are forcing x to increase by 1. We're not telling this person, eat some food and gain a pound of weight, okay? That doesn't quite make sense, right? We're not changing the x and inducing a change in the height, okay? We're just saying that if we have two people and one person weighs 1 pound more than the other, then our prediction for the person that's heavier is going to be this much higher than our prediction for this other person, right? So if there's somebody who weighs 100 pounds, maybe we predict their height to be 61 inches. Okay, I'm making that up, right? So if somebody weighs 100 pounds, maybe we predict their height is 61 inches. If somebody weighs 101 pounds, if there's another person that weighs 101 pounds, then we predict that person's height to be 61.086, okay? Our prediction has gone up by 0.086, which is the amount of the slope. That's what this interpretation means, right? Every time x goes up by 1, our prediction goes up by the amount of the slope, okay? But it's, again, it's for kind of separate things. We're not trying to induce change in the y by manipulating the x here, okay? In a lot of cases, we can't manipulate x, right? I mean, if we had flipped this around, it would make even less sense, right? Like if we're trying to predict someone's weight based on their height, you can't just tell somebody, hey, grow an inch, and we would, let's predict, you know, we can predict how much weight you would gain or lose, okay? That's not possible. We have to, it's more so comparing, you know, this person is this tall, here's another person who's 1 inch taller or 1 inch shorter. You know, how much is your prediction going to differ? That's what the slope means, all right? Here's, you know, as far as the car values go, all right, the predicted prediction line was predicted value is 21,375 times 1215 times age, okay? So our slope here is negative. Our slope is negative 1215, all right? And that means if the age of the car goes up by 1 year, our prediction for the value goes down 1215, okay? And again, you know, in this case, we might even be tempted. It feels like it even makes more sense that a car that just sits there 1 year later, it's going to be worth $1,215 less. But again, it's more so if you have a 5-year-old car, we predict it's going to be worth this much. And if there's another car that's 6 years old, we're going to predict it to be worth $1,215 less. Okay, so we're just kind of comparing values from comparing predictions from, you know, observations with different x values here. I have another typo. The car goes up, oh, goes down. This should say down. Yep, thank you. Thank you for pointing that out. All right, I'll fix that. All right, the intercept, okay? So that's the interpretation of the slope. And this interpretation of the slope is actually very useful in helping us understand the relationship between x and y. Does the negative or positive slope correlate to negative or positive correlation? Yes, absolutely. So if you have a positive correlation, the slope will be positive. And if you have negative correlation, the slope will be negative, okay? Because, so standard deviations are always positive, okay? So standard deviation of y divided by standard deviation of x, this value, sy over sx, will always be positive. This part over here will always be positive. And therefore, the slope is going to depend, the sign of the slope is going to depend entirely on the sign of r. So when r is positive, the slope is positive. When r is negative, the slope is going to be negative. That's a good question, and that is the relationship. So you will never have a positive slope when the relationship is negative. Okay, intercept. Intercept is what we predict the x variable, our predicted value when x is 0, okay? And the intercept is only meaningful if it makes sense for x to equal 0, okay? If you can't have x equal to 0, if it doesn't make sense for x to be 0, the intercept doesn't have meaning, okay? So as far as predicting car value goes, okay, the intercept is 21,375. Can the age of a car be 0? Yeah, that makes sense. If a car has age equal to 0, which would be a new car, our prediction is that it's going to be worth 21,375. Okay, so the intercept here makes sense. All right. Predicting height based on weight, our intercept is 52.397, but you cannot have weight equals 0, right? That's impossible. Weight equals 0 is literally no person, and you have no interpretation for the intercept here. Okay, so this number is meaningless. Okay, doesn't make sense. All right, and so that's that. That's the interpretation of the intercept. It's just our prediction when x equals 0, which may or may not make sense depending on the context of the problem. Okay, so the last section, and then we'll be done for the day, or at least for this lecture, and you guys have a discussion afterwards. There's a bunch of warnings. So linear regression is super powerful, super useful. Statisticians love it. Okay, it's also I don't know, dangerous because it's so useful. Sometimes people will misuse it. Okay, and all of this just says like we have to kind of think through and be cautious. Oh, let me give you your third quiz answer. Third quiz answer for today is A as in apple. Third quiz answer is A as in apple. And that is your last quiz answer for today. A as in apple. All right. Number 1, warnings. Okay. Don't use a linear model to describe non-linear associations. Okay. So you always got to look at a scatter plot first. And then another big warning is outliers can have a big effect on R, the correlation, and if it affects the correlation, it's going to affect the linear regression, right? So you should always check the scatter plot for outliers. So I guess rule number 1, make a scatter plot so you can see if it's linear. Make a scatter plot so you can check for outliers, okay? So there's something known as Anscombe's quartet, okay? And here are 4 plots. And these are technically 4 data sets of x and y variables. And Anscombe, he's a statistician, mathematician. He kind of engineered this data set, and he engineered it in such a way that all 4 of these data sets that are plotted separately, all 4 of them have the same correlation of I forget, 0.8 something. Let's go on Wikipedia. Okay, so all 4 data sets have the same correlation of 0.816. They all have the same linear regression line of 3.0. The intercept is 3 and the slope is 0.5. Okay, and they also all have the same standard deviations and means for x and y. Okay, so it's a rather remarkable feat that he engineered this. Okay, and so they all have the same correlation and they all have the same linear regression line. Okay, but if you look at these, the linear regression line really only makes sense for this first data set. Okay, this one is kind of your typical. We have scatter around the linear regression line. Linear regression makes sense for this, right? It does not make sense for this. This is clearly, there's a relationship, but it's not linear. There's a curved relationship, and trying to summarize it with a straight line is probably a bad idea, okay? Because the straight line says, you know, we're going to predict as x gets higher and higher, we're going to predict y to continue going up, right? But if you were looking at this and somebody says, okay, what are you going to predict the value of x to be when you're over here? you're gonna predict that the y goes down, right? Just looking at this relationship, it looks like y is going to come down. Honestly, we don't know what's going to happen in the future. We don't know what, I mean, it could turn around and stuff like this. But using a straight line doesn't really make sense, right? If we had to predict, if we were using our sense of like make a pattern, we would predict, you know, that the line goes in this direction down here. Okay, over here, what's going on? Okay, these dots look like they are in a perfect straight line. Okay, if we had gotten rid of this one, if we get rid of this one, these would be like in a perfect straight line, and we would have a correlation of 1. Okay, but we've got an outlier. We've got an outlier, and that's throwing everything off. Okay, and somehow this one outlier is enough to cause the correlation to become 0.816. Okay, has the same correlation as this amount. Okay, these two have the same correlation overall, but it doesn't make sense to use this linear regression line, right? This might be a typo. Somebody might have entered the number in wrong, and that's why it's up there, okay? Probably you feel like it should be along here, and then if we had to make predictions, it would be right along this line, right along here, okay? If we had to make a prediction. So this is no good. Okay, over here, what's going on? Okay, here, this one's like the worst, but this is a mistake people make. We've gathered X. Pretty much all of our observations have X equal to 8. Okay, pretty much every single observation in our data set has X equal to 8. And then we have one observation where X is like 18 or 19. And based on that one observation, we're creating our entire trend line, right? This would be kind of like, imagine, so earlier I did the silly example, and I said, what's the relationship between income and the number of fingers, right? And there's no relationship, right? And if we said X is the number of fingers, maybe in our data set we have 10 people, or maybe 20 people, and all 20 people have 10 fingers, right? And then we got a wide range of incomes, and we would find no relationship, right? We would get a plot where everything's in a vertical line, everyone's got the same number of fingers, and they've got different amounts of income. And we'd say, okay, there's no relationship. But let's say someone comes along, and for this person happens to have 11 fingers or 12 fingers. They have an unusual amount of fingers, and let's say this person is very financially successful. They've made a lot of money, okay? And then suddenly, by including that one observation with a different X value, everybody else has the same X value, and this one person has a different X value, and a different Y value is very high or something. Now we're going to say, oh, now we're going to see a positive relationship between number of fingers and income, and it's going to look like, oh, the more fingers you have, that's associated with higher income. And that would just be a ridiculous conclusion to make, and it's silly to make an entire conclusion based on one observation. But that happens a lot. People do business operations, and almost everybody is operating in a kind of this very tight, narrow range, and then you're trying to predict what's going to happen out here, and you have like one observation, one order that is like way bigger than everything else, or way smaller than everything, just very different than everything else, and that's going to be that's going to inform you, or sometimes businesses want to use that to try to make decisions about everything in between, and that kind of conclusion does not make sense. All right, so I'm just kind of given like little one-liners summarizing all of that, what I've said here. But basically, linear regression only makes sense for this, and these other three examples, even though they have the same correlation in the same linear regression line, it does not make sense in those situations. Okay, other warnings. Correlation is not causation. We've talked about this, but just because two variables have an association, that is not going to be enough to draw a cause and effect relationship. Okay, and as humans, we frequently draw cause and effect conclusions, right? We see two things happening together, and we're very quick to make cause and effect conclusions. And again, this goes back and says you can't do that. You cannot. You can't make that conclusion. So just be careful. You need to have somebody who understands a little bit more of the system there. Okay. And then the other is don't extrapolate. Don't make predictions beyond the range of the data because we're not sure that the linear trend will continue beyond the range of the data. And so here's a silly example. Silly example is, imagine you have, you are measuring the height of your child. See, let's say you have a kid, and from age 2 to age 10, you measure your child's height every single month or every single year, and they keep growing. All right, from age 2 to 10, they keep getting taller and taller and taller. And this trend has held up very strong for the last 8 years. Okay, so a trend that has existed for the last 8 years, you'd say, wow, seems pretty good. And you might be tempted to say, oh, well, in that case, when the kid is 60, he's going to be 20 feet tall or something like that. Okay, and of course, we don't know what's going to happen. As far as height goes, we know that people continue growing until they're around 16, 18, 20, something around there, and then they stop growing and they stay their adult height for a large portion of their life, and then maybe in their later years they lose a little bit of height. Okay, but we have no idea. Just because a linear relationship has existed for the past 8, 10, 20, 50 years does not necessarily mean it's going to, it could take off and rocket up. It could continue straight. It could do that. It could, okay, who knows what's going to happen, right? So anytime we're trying to predict the distant future, it's very dangerous in that we don't know if the, just because a relationship has held for the last decade or so does not necessarily mean it's going to continue on into the future. And so, the example of a child growing is silly because it's something that we're all familiar with, right? But if you bring in something that you're unfamiliar with, the child growing, that trend holds for a decade or so before it levels off. And in a lot of places, in business, they might say like, oh, this trend has held, we've had this kind of growth for the past 10 years, and it might be tempting to assume that it continues to hold into the future. And the answer is we don't know. It could be any of these situations, one where it rockets up, one where it turns around, one where it levels off, or it could continue going straight. So who knows? Okay, so that's called extrapolation, and it's a grave sin of linear regression. So don't do that. There's one more definition, and this is called R-squared, and that's called the coefficient of determination. You just take your correlation value and you square it. You're going to get always a value between 0 and 1 because negative values, when you square them, become positive. So correlation goes from -1 to +1, and R-squared will go from 0 to +1. And the technical definition is how much variation in the response variable is explained by the explanatory variable. And it's a little bit of an odd definition, but kind of the big takeaway is that larger R-squared values mean a stronger relationship. And this is a value that often gets reported in papers and things like that when they're talking about the relationship, a linear regression relationship. You might see the R-squared value reported rather than R itself. And we'll just kind of leave it at this loose definition. Again, if you choose to major in statistics, you'll get into a little bit more of the meaning of this, and you'll see the formulas and all of that. And it is a neat relationship. But as far as the intro class goes, we're going to just keep it simple and say larger values of R-squared mean a stronger relationship. But it's something that does appear in the literature, and it is something that you should be familiar with. All right, we'll end here for today. On Wednesday, we'll pick up on chapter 5, which will introduce us to probability. And we'll see you guys then. Don't forget to take your viewing quiz, and lab 1 is due tomorrow. So that's all. We'll see you guys there. Question 3 on the quiz was A as in apple. I'll say that one last time, and that will be it. Thank you, guys.